Hello APC Mechanics students, today we'll solve the past paper of RQ 2002, exercise number 1, skipping the directions and starting with the text of exercise 1. A crash test car of mass 1000 kilograms moving at a constant speed of 12 meters per second collide completely elastically with an object of mass capital M at time t is equal to 0. So time t equal to 0 represent the instant of collision. The object was initially at rest. The speed v in meter per second of the car object system after the collision is given as a function of time in seconds by the expression v is a divided by 1 plus 5t. In part A, we need to calculate the mass of the object. So if you think about it carefully, the only thing that we can do in order to determine the mass of the object is the conservation of linear momentum. So let me say apply conservation of linear momentum. Now, what does the conservation of linear momentum states? It states that P initial should be equal to P final. Now, initially before collision, what momentum do we have? We have the momentum due to the car, which is the 1000 kilograms multiplied by 12. And after collision, we have, so if you consider the text, this is an inelastic collision, and after collision the car sticks to the object, forming a car object system. So we have a combined mass given by 1000 plus the unknown mass that we wish to calculate multiplied by the speed v. Now here, what's the type of this equation? This is the linear equation which promotes us to calculate only one variable, which is basically m. Then v can be determined by referring to this expression and replacing t is equal to 0, which is the instant of collision. Now v is given by 8, so let me say v computed at t is equal to 0, that would be 8 divided by 1 plus 5 multiplied by 0, which is basically 8 meters per second. And here notice that the speed drops from 12 into 8 due to the increase in inertia, due to the increase in mass, so that would be 12,000 equals to 1000 plus m multiplied by 8, and we're solving for m, so that would be 12,000 is given by 8,000 plus 8m. Now m in this case is given by 4,000 divided by 8, and that would be given by 500 since everything in the SI. Then the mass of the object is given by 500 kilograms. Then we have that the mass of the object is given by 500 kilograms. Now, assuming an initial position of x is 0, determine an expression for the position of the car object system after the collision as a function of time. Now here, because we're interested in determining the position, not displacement, so it's better to represent our quantity as unbounded integral. Why I'm talking about integral? Because we're interested in determining the position of the car object system after the collision, and we have the velocity. We know that the variables of motions x, v, and a, so here that would be a derivative, that would be a derivative, and that would be an integral, and that would be an integral. So if we wish to determine x from v, we should integrate. And as I was saying that the integral in this case, it's better to represent it as a free integral since we are interested in the position. However, you can also proceed with the displacement and then utilize that delta x is given by x final minus x initial, and x final would be our position. Now that would be the integral of, now the function that we have is given by 8 divided by 1 plus 5t, and we're integrating over time. So how we're going to integrate this function? We can proceed by change of variable. So let me say let a new variable u is given by 1 plus 5t, which means the differential u would be the derivative of this, which is basically 5 multiplied by differential of t, which means that differential of t is given by du divided by 5. Now completing the integral here, that would be 8 divided by u multiplied by du divided by 5. So that would be 8 over 5 integral of 1 over u du. Now the integral of 1 over u du, that would be ln u. And we don't forget the constant c. But remember that initially we're integrating over t, so u again should be replaced by t, so that would be 8 over 5 ln 1 plus 5t plus the constant. Now remember that the constant is determined by initial conditions. Now initially, assuming an initial position of x is equal to 0, so x is equal to 0 is 1 initially, which corresponds for t is equal to 0, and that would be 0 equals to 8 over 5 ln 1 plus 0, because t would be 0, 0 multiplied by 5, that would 0 plus c, and we know that ln 1 eventually is 0, so basically which makes c to be 0. Then the position in this case of the car object system after the collision is given by x is 8 over 5 ln 1 plus 5t expressed explicitly in terms of time. Now determine an expression for the resisting force on the car object system after the collision as a function of time. We know that the force basically is related to acceleration, since the only given is given by the velocity. Now here, even if it's not mentioned in the text, we're assuming that the collision occurs on a level surface, which means that if it happens to have the normal push, it would be balanced by the pull of gravity. So let me say that the resisting force given by F can be dictated by Newton's second law, which is ma, and A can be determined, so here let me also mention the following: x cannot be determined by V using kinematics because V is not linear or constant, and here for the same reason, because V is given as a complicated irrational function, then the way to determine A is using calculus, which is dV by dt. That would be md by dt. Now here I have done a mistake. Now what does this mass represent? Because we are talking about the car object system, then we should include the total mass. Now one of the masses is capital M, and let me name the mass of the car to be small m. So that what would be m plus capital M multiplied by A, and that would be m plus capital M. Alright, dV by dt, which is m plus capital M d by dt of the function that we have, which is basically 8 over 1 plus 5t. Now here, so how do we derive this function? This can be understood as u over v, and the derivative of u over v is basically u prime v minus v prime u over v square, in which u is 8, u prime would be 0, v is 1 plus 5t, and v prime would be 5. So if you replace that, so this would be given by a fraction 1 plus 5t square in the denominator, and that would be 0 multiplied by 1 plus 5t minus 5, which is v prime multiplied by 8. So let me replace it here. That would be m plus m multiplied by a big fraction. In the denominator we have 1 plus 5t square, and basically 0 multiplied by 1 plus 5t minus 8 multiplied by 5. Now we can replace the masses. One of the masses is 1000, the other mass is 500, multiplied by minus 8 times 5, which is minus 40 over 1 plus 5t square. Now that would be minus 40 multiplied by 1500 over 1 plus 5t square, and that would be basically minus 60,000 divided by 1 plus 5t square. Now here no need to represent any unit, because the resisting force itself is expressed in terms of another parameter. And if you want to put in it, that would be newtons. Then the resistive force in this case is given by F, which is minus 60,000 divided by 1 plus 5t squared. Now here, why do we have a minus sign? Because simply the force is a resisting force. If they ask us to determine the magnitude of the resisting force, then we should eliminate this minus sign. Now, before referring to power D, if you look carefully, F is given as function of time. Why this is healthy? Because especially in the context of collision and momentum, we can determine the impulse, which is basically given an integral of F over time. And indeed, in part they're telling us to determine the impulse delivered to the car object system from 0 to 2 seconds. 0 represents the instant directly or at the moment of collision, which represents the car object system. 2 is equal to 2 seconds, governed by F is given by this expression. Then J would be given by the integral from 0 to 2 of F dt, which is given by integral from 0 to 2 of minus 60,000 divided by 1 plus 5t squared dt. Now minus 60,000 is a constant, it can be dragged out, and upstairs we would left by 1 over 1 plus 5t squared dt. Now again, how can we utilize this integral? By doing a change of variable. So let me say again, resetting our variables, let u be 1 plus 5t, and in this case du is the derivative of this, which is 5 dt, which means dt would be given by du divided by 5. Now that would be equal to minus 60,000. The integral, now here I need to mention something very important, that would be 1 over u square du over 5. Now here we are not allowed to place any boundaries for the integral, simply because these boundaries are defined for t. Now when we integrate for u and we replace u by t, then we will replace the values of the boundaries. Now that would be minus 60,000 divided by 5, and this irrational function can be utilized as a power function given by u to the power of minus 2 du. Now how to integrate this? This is easily, we increase the power by 1 would be minus 1, and we divide by the final power. That would be minus, so 60,000 over 5, that would be minus 12,000 multiplied by u to the power minus 1 divided by minus 1. That would cancel, and that would be 12,000 divided by u, and here we have boundaries that are undefined at this moment, and that would be 12,000 divided by 1 plus 5t. Now since u has been resumed again by t, we can say it's being computed from 0 to 2. So what does this mean? We're gonna compute this function twice, one at 2 and one at 0, and we'll do the difference between them. That would be 12,000 over 1 plus 5 multiplied by 2 minus 12,000 over 1 plus 5 multiplied by 0, and plugging this expression on the calculator, we're gonna have a value given by minus 10,909, and the unit of impulse is basically Newton second or kilogram meter per second. Let me use a Newton second, and here it's negative. That's fine, because we know that the impulse is a vector quantity. So in this case, then the impulse according to the tax delivered to the car object system is given by minus 10,909 Newton second. And that's it for me in this video, guys. See you soon in a new one.